Welcome back, AP Statistics. This is part 3 of chapter 16. We're going to be talking about another probability model today. This is the binomial probability model. So when we're concerned about the probability of a certain number of successes in a certain number of Bernoulli trials, we would use a binomial probability model. So this is a little different than the geometric probability model. We're concerned with not the how long it takes to get the first success. We're thinking of the probability of getting a certain number of successes out of a finite number of trials. The binomial model requires two parameters. So just like the geometric probability model requires one, namely the probability of success, the binomial model requires two parameters, n, which is the number of trials, and p is the probability of success. We denote the binomial probability model, this little notation right here, binom np. And here are the details on the binomial model. Like I said, n is the number of trials, p is the probability of success, and Q is the probability of failure. Also, 1 minus P is the same as Q. Q and P are complements. And X is the number of successes in N trials. And X is the random variable. It counts the number of successes. So again, we're not finding the odds of it taking 5 trials to get the first success, like in geometric probability model. We're finding the odds of getting, say, 3 successes out of 5 trials. Okay, so this is a bit different. So the probability that we get a certain number of successes, the odds that the variable equals that value, is equal to this kind of sort of mess right here. And this N and X is this fella right here, which you may be wondering, what on earth is that? We'll get to that in just a moment. But the mean for this random variable, distributed according to the binomial model, is n times p, which makes sense if you think about it. If we have some percent probability of success and some number of trials, then that percent of the trials is going to be our mean. Not too terribly complicated. What is more interesting is the standard deviation, which, just like the geometric probability distribution, is not immediately obvious. And we'll just take that formula for granted and move on. So that mysterious formula that I showed you on the last slide with the factorials in it, that is a combination. You saw it in this form, which is very difficult to typeset, as you can tell. This is the same as n choose r. This is n up top, r in the bottom, no fraction bar, but parentheses around. So we have NCR, and that is the number of combinations of R objects we can select from n total objects. So for example, 10C3 is the number of groups of 3 students a photographer could choose from 10 student council members for a photo op for the local newspaper. So we're just choosing a certain number of objects from a total. In the binomial probability model, the combination accounts for the number of ways you could choose your successes in n trials. This means that the successes don't have to all be bunched together. There's not one way to achieve our successes. There are n choose r ways of choosing our successes out of the total trials. So let's use the binomial probability model. The communications monitoring company Postini has reported that 91% of email messages are spam. Suppose your inbox contains 25 messages. What are the mean and standard deviation of the number of real messages you should expect to find in your inbox? And then, what's the probability that you'll find only 1 or 2 real messages? Okay, so first we're asked to find the mean and standard deviation. And those formulas you just saw. We're going to let X be the number of real messages in the inbox. Then the expectation, that's the same as the mean, is n times p. N is 25, there are 25 trials, and the odds of success, that is a real message, so fail is spam, success is real. So we have 25 times 0.09, and that would be 2.25. So we only expect between 2 and 3, leaning on the side of 2, real messages. Aren't you grateful for your spam filter? Anyway, standard deviation is going to be this interesting entity right here, square root of NPQ, which is the square root of, wait, how did we get this 2.25? Well, that's from N times P. What I'm just going to do is say 2.25 is N times P because that's how we found 2.25. We did N times P. So we have 2.25 times our new character here, Q, the probability of failure, which is probability of getting spam, and that would be 1.43 after we multiply inside and compute the square root. Okay, now we need to find the probability that only 1 or 2 real messages are what we get. And considering that our expectation is a little over 2 messages, this should be a decently likely event. So the probability of 1 or 2 real messages is equal to the probability that x equals 1 plus the probability that x equals 2. We can write those as combinations. We'd say 25 trials, choose 1. We have 1 success and not 24 fails. All right, so we have probability of success, number of successes, probability of failure, number of fails. Okay, and that's using the formula. Then we have probability x equals 2. 25 choose 2. We have 25 trials. We choose 2 successes. Here's my odds of success, number of successes, odds of failure, number of failures. And that turns out to be a little over half. So we are more likely than not of getting 1 or 2 real messages. Now we're going to go back to our problems involving blood donors. Suppose 20 donors come to a blood drive. Recall that 6% of people are universal donors with that O-negative blood type. Here are 2 questions. What are the mean and standard deviation of the number of universal donors among them? And 2, what's the probability that 2 or 3 are universal donors? Okay? Now, before we go on to this, there are some things we need to check off before we do this problem. So last problem we did, we just did the computation and made some assumptions. Let's explicitly state the assumptions we need to make in order to use the binomial probability model. Okay? So we're going to determine if these trials are in fact Bernoulli trials. This will only work if the trials are truly Bernoulli trials. So there are 2 outcomes. We have success, O-negative, failure, other blood types. Okay, there are 2 outcomes. Perfect. The probability of success is 0.06. The people have lined up at random. We're assuming randomization scrambles things. So we have a fixed probability of success and independent trials. And the 10% condition. Trials are not technically independent, fine, because every population you'll ever run into is finite, and once we take someone out of the population, the trials are not technically independent, but fewer than 10% of all possible donors are lined up. So before I said the trials are independent, well, that's mostly true. The trials are not truly independent. However, we are sampling fewer than 10% of all donors lined up. So yes, you can assume independence, as I said before. Let X be the number of O-negative donors among the 20 people. All right. X is the number of donors out of 20 people who have O-negative blood. And finally, we can model our random variable with this setup. Binom. And we have 20 is our size of our sample, and 6% is our odds of success. All right, so we have identified a random variable and stated, yes, it fits this model. Let's get to work. We can do this efficiently on a graphing calculator, so you don't have to type out all those combinations and exponents and all that. It's actually a really easy operation once you get used to it. So in distribution, just like before, you can find binom PDF. That's the probability density function for the binomial model. And that receives 3 arguments, right? That receives 3 arguments. The first argument is going to be the number of trials, n. P is the probability of success, second argument, and x is the number of successes. So just like the shorthand binom n and p, binom PDF has n and p as well, but also you state the number of trials you want to be successes. And then the calculator takes care of that. So we're going to solve problem number 2 on the prior slide using the graphing calculator. So let's go to distribution. We're going to go down near the bottom, and this is a binom PDF. We're going to first find the odds of exactly 2 successes. So we have 20 trials, odds of success is 0.06, and we want 2 successes, and we hit paste. We're going to add this to, let's do it again, distribution, go near the bottom. We have binom PDF, and we would say 20 trials, odds of success is 6%, and now we want 3 successes. We hit paste, and now we hit enter, and it's a little north of 31%. So let's try a slightly different problem. You may have noticed there is a binomial CDF on the calculator, not just a binom PDF. So how do we use the CDF? Well, very similar to how we would use the geometric CDF. So in distribution, you can find binom CDF, C referring to cumulative, so it's the cumulative density function for the binomial model, and that receives 3 arguments. Binom CDF is N, P, and C. And this is what's cool. N is the number of trials, duh. P is the probability of success, same old, and C tells the calculator to accumulate the probabilities of no successes, 1 success, 2 successes, all the way up to C successes. So instead of doing a bunch of computations, binom CDF does many at once, and you specify how high you want to go. So we're going to find the probability of finding up to 3 universal donors. That could be 0, 1, 2, or 3. And we're going to refer to the problem 2 slides back, which is the problem about those universal donors and the likelihood of getting one and how many are we going to get out of 20 trials. Okay, back at the calculator, we're going to go to second distribution. We're going to go to binomial CDF, so binom CDF. And we're going to say we have 20 trials again, just as before, and our odds of success is 0.06, and the X value is going to be 3. Now, this is going to tell us the odds of getting 0 successes, or 1 success, or 2 successes, or 3 successes. So we're going to hit paste, and there you go. Very high likelihood of having up to 3 successes. So here's some practice from our textbook using not only the binomial probability model, but the geometric model from the prior lesson. Here we go. So the Pew Research Center reports that it's able to contact about 76% of randomly selected houses drawn from the telephone surveys. All right, so suppose a pollster has a list of 12 calls to make. So our sample size is going to be 12. That's going to come in handy. Why can these phone calls be considered Bernoulli trials? There are a couple things we need to look for. There's a clear success and failure. You either get someone on the other end or you don't. All right, so there's contact versus no contact. That would be success fail. And we have 76% chance of success. Those odds do not change. And even though every time we call someone, we remove someone from the population, we can assume independence because 12 is significantly less than 10% of the population Pew Research would be calling. Pretty sure that's a safe assumption. So let's look at part B. Find the probability that the 4th call is the first one that makes contact. So we are trying to find the likelihood that not the first or second or third, but the 4th call is the first success. That is a geometric probability model problem. Give this one a go. Feel free to pause the video and unpause when you're done. Okay, I'll assume we're ready to continue. We're going to let X be the number of calls until first contact, probability x equals 4 is, well, here are my odds of failure. We want 3 of those followed by a success. Multiplying that out, you have a little north of 1%. Now let's go to part C. Find the expected number of successful calls out of the 12. Okay, this is a new feature. We only have 12 trials, and that becomes important. So we need to think about this differently. This is no longer a geometrically distributed random variable. We need a new random variable, and that random variable is going to fit a binomial distribution, a binomial model. So we're going to let y be the number of contacts in the 12 calls. Then the expectation of y, which is a different variable, it is distributed according to the binomial model. There are 12 trials and a odds of success of 76%. So we do n times p is equal to 9.12. Okay. Now, let's find the standard deviation of the number of successful calls. All right, so I took this one on since we needed a new random variable. How about you try this one? Standard deviation of the number of successful calls. Pause the video and unpause when you have an answer. Okay, let's continue. The standard deviation of y is going to be this 9.12, that's n times p, times q, the odds of failure, and we would square root that. We get about 1.5, a little short of 1.5. Okay, now let's go to E. Find the probability that exactly 9 of the 12 calls are successful. All right, this is going to use the binomial probability model. Give this one a go, pause the video, and see if you got it right. Okay, let's continue. Probability of 9 successes, again, we're using the random variable y. X is a geometrically distributed variable. Y is a binomially distributed variable. So we got to keep that straight in our heads. Probability that y equals 9. I'm going to use binom PDF. There are 12 trials, 76% chance of success, and I want the odds of exactly 9 working out, and that is a very likely event. All right, now 9 is 75% of 12, so 76% chance of success. Well, we're expecting about 9 out of 12 to work out, so this is going to be a likely event right off the bat. That should not surprise us that we already have a 1 in 4 chance of landing exactly on 9 successes. Now, here's a different question. Find the probability that at least 9 of the calls are successful, all right? Now, I'm going to take this one on because there's a creative way of doing this, okay? At least 9 of the calls are successful. I'm going to use binom CDF here, and I'm going to use binom CDF because I can do this in one computation. Remember, binom CDF counts the probability, finds the probability of getting 0 or 1 or 2 or whatever, counts all the way up to you specify number of successes. So if I want the odds of at least 9 calls being successful, what's the complement of that? Well, the complement would be you get either 0 or 1 or 2 or 3 or all the way up to 8 successes. And that's something that can be computed really efficiently using binom CDF. So I'm going to say probability that y is greater than or equal to 9 is equal to 1 minus the probability that y is less than 9. Okay, so I'm going to use the complement of the event. And that would be 1 minus binom CDF. I have 12 trials, 76% chance of success, and I want to find the odds of 0 successes, or 1, or 2, or 3, or 4, or 5, or 6, or 7, or 8. I want to add all those probabilities together, and we can handle this in one fell swoop, and it's about 32% chance.